Okay, welcome back to Calculus 1. This will be the 10th lecture of the course. And today we're going to talk about implicit differentiation. So let's call this section 2.5, implicit differentiation. Okay. So up to this point, we've differentiated functions that have all been in explicit form. So for example, y equals 3x squared minus 5, right? This is an example of a function that's in explicit form. So what do we mean by explicit form? What we mean is the function is written, so here what we mean by that is that the variable y here is written explicitly as a function of x. So y is written explicitly as a function of x. All right, and this is what we're used to, right? So normally when we talk about functions, normally they kind of are in explicit form. Typically, that's what we're kind of used to. Another example would be like y equals 1 over x. Here, y is explicitly written as a function of x. But we could, in the case of this latter example, for example, we could write this. We could write this in a different way, right? We can multiply both sides by x, for example, and we could have something like this: xy equals 1. So when we write it like this, what we're saying is basically the function y equals 1 over x is defined implicitly by this guy. So here, this is an implicit function of x, sorry. So y is y is implicitly a function of x in this example. Okay, when it's written like this. Okay, so in examples like this, where you have functions written in an implicit form like this, finding the derivative of y with respect to x is a little bit different. So in this case, in the case of xy equals 1, right, we could go and calculate, we could find the derivative here. I mean, it's a simple matter to just rewrite it as y equals 1 over x, right, and then to calculate dy dx. So that's not the interesting case, right? That's not if a function's written in implicit form like this and it's easy to convert it to explicit form, might as well just do it and then calculate the derivative using the traditional means, right? But what happens if instead you have functions written in the functions maybe that look like this: 3y squared plus 2xy plus y cubed x squared equals 10. Something like that. I'm just making this up off the top of my head here. Something like this, so we could assume that y is implicitly a function of x. But when you look at this, I mean, it's not obvious how you would proceed. How you would go about writing this explicitly as a function of x. So not easy. We'll just say that not easy to convert to explicit form. Okay, so this is an example where you've got something where we'll say y is implicitly a function of x here. And it's not easy to convert to the explicit form that we're used to of y equals something. Okay, but let's say for the sake of argument that we have a function like this, but we're still interested in knowing dy dx. So maybe we still want to know dy dx. How do we go about that? Right, and that's kind of the subject matter of this section. Okay, so to find dy dx, okay, so to find dy dx, it's important to realize that we are differentiating with respect to x. Okay, with respect to x. Okay, so to find dy, it's important to realize that we're differentiating with respect to x. Now, clearly the differentiation is the same with terms involving only x. So, for example, we don't have one in this example, but let's say we had 2x squared up front here. Let's just, for the sake of argument, this term here, differentiation would be just like before. Nothing new there. It's all these other terms where you have a y in the mix. That's where the implicit differentiation is going to come into play, right? So it's important to realize that we're to find dy dx, we will be differentiating with respect to x. Terms with only x will be the same as before. Okay. All right. But any term that involves y, the variable y, will have to do something different. So terms involving y will be treated differently. Okay, now they'll be treated differently, but there's a straightforward mechanism for it, right? So it's basically what we'll be doing is we'll be using the chain rule. Okay, we'll go through a ton of examples and you'll see how this works. But so that's the basic idea, right? So you start with a function that's implicitly where implicitly you have y as a function of x, right? And it's not easy to convert to explicit form. That's key. If it is easy to convert to explicit form, you're better off doing that and then just treating it like normal. But in the examples where you can't convert it to a y as a function of x explicitly, then you have to proceed with this process. Okay. Now, remember, we're always differentiating with respect to x, right? And terms with only x will be the same as before. They'll be treated the same as before, just like the regular derivatives we've been doing all this entire time. But terms involving y will be treated differently, and specifically we'll be using the chain rule on them. So let's talk through an example and see how this works. Okay, let's kind of walk through here. So clearly, right. So we're used to this kind of thing, right? Find the derivative of x cubed, right? So this is, we're differentiating with respect to x, and the expression we're differentiating only contains x. So this is straightforward, same as before. Okay. But what happens if we differentiate with respect to x something like this? Okay. Right. So when we look at this, we can see that this is going to involve the generalized, this is like the power rule, right? Okay, that would be like if this was, the item above, we would say, oh, simple, like it's a power rule, so the 3 comes down, and then 3 minus 1 is 2, so it's 3x squared. Simple, right? But because we're differentiating y cubed with respect to x, we have to think about this differently. And so the way we think about it would be, we are going to assume that y is defined implicitly as a differentiable function of x. So let me write that down, because that's kind of the key to sort of understanding this. We assume that y is defined implicitly as a function of x. Okay, so the way we want to treat this is we would kind of think of this as there being an outside part, right? So this is like u to the n, right? So we would differentiate that like normal, so it'd be n u to the n minus 1, right? But then because u itself is a function, right? In this case, we're assuming y is defined implicitly as a function of x. there would be this other piece here, u prime, right? So that's how the chain rule would work in the case of the power rule, right? And so that's what we want to do here. So let me rewrite this and let's actually differentiate this properly, right? And so what we would say is we would differentiate the outside piece here as 3y squared, right? But then y is itself a function of x. And so what we would need to have in addition to that would be the derivative of y, right? We'd have to differentiate that inside part, which we're assuming is y. And so the way we would do that, I mean, we don't know what it is, so we can't actually do it. We're gonna just implicitly do it. So what we would say is times y prime. All right, this is the prime notation. All right, another notation that you'll see, you know, maybe you would write it, let me put it like next to it here, actually. It's there. So you might write it like this, 3y squared, right? That's the derivative, the outside part here, but then we assume there's an inside part as well, but we just don't know what it is explicitly. And what we would write then is dy dx. Okay, I actually like this form better. I just like the dy dx notation here. It just seems more, it's a little more intuitive for me personally. You also don't run into this problem like all these y's with these superscripts that look like ones. Okay, so that's the idea. That's the idea. So basically, whenever we differentiate a term that involves a y, we treat the outside function at face value, almost like you pretend that it's an x. You differentiate it, like in this case, we differentiated y cubed as 3y squared. But then we add on this other piece, this y prime, or better, dy dx, to signify that there's this implicit part of y that we don't know what it is, so we symbolically represent it by the derivative notation. Okay, let's take another example here and we'll see how this works here. So here we want to differentiate x plus 3y. So something like this. Well, there's two terms here. Let's just break it up and let's be real thorough here in the way we write this out. Right, now this first term is just derivative with respect to x of x, so that one's normal, right? You would just get a 1 when you differentiate that. This other term, here's where we have to use what we just described, right? This implicit differentiation. So first we treat the outside as though it's like a normal x variable, but then we assume this interior piece of y here is a function. We're assuming it is, you know, defined implicitly as a function of x, and we treat that separately. So the outside function here would just be, you know, the derivative of 3 times y, which would just be 3, right? And then we have to differentiate y with respect to x, and so of course we would just write dy dx. Okay, or y prime if you prefer that notation. Okay. All right. Okay. And this can, you know, these have been pretty easy so far, but these can get as complicated as you like. So let's take one that's a little more involved. What about this? What if we want to differentiate this term, x, y squared? All right, so here we've got a product, right? You've got the product of x times y squared, right? So this would be an example where you have to use the product rule. Okay, so we would think of this as the first function and then y squared as the second function. And so the product rule says it'd be like x times d dx of y squared plus y squared times d dx of x. All right. So then this piece here, the x obviously stays as is, and then we would differentiate y squared as just 2y, right? But we're differentiating y with respect to x, so this would have to involve the chain rule, and so we would tack on a dy dx right afterwards. And then plus, now the y squared is just y squared, no derivative there, and then the derivative of x is just 1. Okay, so altogether you would get what? 2xy dy dx plus y squared. That would be another example. Okay, all right, and we'll get into sort of the value of this in a second, right? But this is just kind of the method, like how do we go about doing this? Okay, and so let's summarize the method here real quick, right? Let's summarize the method. Okay, so maybe the first thing you would do is basically differentiate both sides. If you're given an equation in implicit form and it's not easy to convert it to explicit form, how would you go about identifying dy dx? Well, first thing you would do is you would start by differentiating both sides with respect to x. Okay, and then once you've done that differentiation, it's very often the case that you can sort of separate the variables in a, much easier, right? And so what you'd want to do after you differentiate with respect to x is you would want to collect all terms involving dy dx, right? Collect all those terms, and then factor and solve for that, for dy dx. Okay, so this is kind of the method, right? Okay, so let's take a look at a more concrete example. Okay, so find dy dx for, we'll say y cubed plus y squared minus 5y minus x squared equals -4, right? So here we have an actual equation, and this is an equation involving x's and y's. So, and it's not, I mean, you clearly see it's not obvious how we would go about solving this equation for y, right? But we're still interested in identifying the derivative of y with respect to x. So how can we do that? Okay, so first thing we want to do is we want to differentiate both sides with respect to x. So basically what you're going to say is you're going to say, okay, d dx, both sides, y cubed plus y squared minus 5y minus x squared equals d dx of -4, right? So we're going to differentiate both sides. All right, now, of course, right, how we do that, we would want to break all these terms up, so I'm going to do that. So d dx of y cubed plus d dx of y squared minus 5 d dx of y minus d dx of x squared equals d dx of -4. Right, so the whole thing, everything kind of broken up there. All right. Then we go ahead and just start doing the differentiation. And so we would differentiate this guy as 3y squared. Now, again, we're differentiating y with respect to x, right? So you've got to think of that y variable as having an inside part, and we're going to use the chain rule, and so we would identify basically whatever y prime happened to be. In this case, we don't know, so we just write dy dx. Okay, plus, and now here we would do the same thing. It'd be 2y times dy dx. Okay, and then it's minus 5, and then what do we have here? Well, the derivative of y with respect to x would be just, in this case, 1 times, and then of course you got to use the dy dx there. And then here this is minus d dx of x squared, so this would be minus 2x, right? Now again, here we're differentiating x with respect to x, so no need to have the chain rule come into play. And then over here, this is just 0, right? The derivative of constant is always 0. There you go. So that's kind of like the step 1. right? So just go about differentiating both sides with respect to x. Now, really, the only thing that we've said here that's different, right, from practically speaking, right, is this addition of this dy dx, this chain rule sort of approach to differentiating y variables with respect to x. Okay, so that's the only thing that's really changed here. Okay, so then what we want to do is we want to collect all the dy dx's, right? We've kind of got that for the most part here already, but let's just make it real explicit here. So you've got dy dx, and then you've got this guy, 3y squared plus that guy, 2y minus 5. Okay, and then you've got minus 2x equals 0. And so let's just toss that over to the other side of the equation. All right, so we've factored out all the dy dx's. And then what we can do is we can solve for dy dx, which in this case is literally just a single step. Right, we divide everything by this piece of it here. So it'd be 2x divided by 3y squared plus 2y minus 5. Okay. All right, so that is, so this would be dy dx in the case of this given this equation, right? So this equation is has x's and y's all kind of mixed together, and it's not written explicitly as, you know, y is a function of x. Instead, it's implicit. It's an implicit form, and given that form, if we're interested in finding dy dx, we kind of go through this process, and this is what it looks like. This is the derivative of y with respect to x of that equation. Okay, so let's talk about this equation here. Let me do a quick sketch of what this looks like. Okay, so let's so it cuts through there, and it comes up a bit. Sorry, I'm just drawing this really quickly, and maybe it goes through down here. Yeah, so this function looks like this. Okay, so this is the x-axis, and this is the y-axis. So you know, clearly this is not a function of x. So, and I mean, obviously, it's not a function of x because it would fail the vertical line tests at lots of places, right? So, nonetheless, we can identify dy dx for this equation, which is, you know, basically what we've got here. All right, so we can identify dy dx for this equation, and we can use this derivative here to identify the slope of this graph at various points on it. So let's consider this point. There's a couple points of interest here. I've got 1, 1, and then I've got 2, 0, and then down here I've got 0. Let's see, what is that point? Yeah, so 0, negative 3. Okay. So let's take a look at this point to start with. So consider that point, 2, 0. Maybe I want to know the slope of the tangent line at 2, 0. Okay, so what I can do is I can say, all right, I'm going to evaluate. So I want to evaluate dy dx at 2, 0. Okay, so dy dx evaluated at 2, 0 would be, you just basically take this thing, I'm just going to write this real explicitly so that it's clear what's happening. I'm going to evaluate that at 2, 0. And so that means basically everywhere I've got an x, I got to plug in a 2. Everywhere I've got a y, I plug in a 0. And so what do I get? I get 2 times 2 up top, and then 3, and then, you know, a lot of these terms are going to zero out. Okay, and so what I end up with here is negative 4/5. All right, so here you get the 4, and down below you got a negative 5. And so what this is saying, what this is telling me is that the slope is negative 4/5 at the point 2, 0. Okay. All right, that makes sense. I mean, it looks reasonable. Certainly could buy that that's 4/5 there. What about this point here? What about 1, 1? You know, if you look at that, what you'd be inclined to say is that, well, it looks to me like the tangent line would be vertical there. It looks, it's probable that that the tangent line is going to be vertical. So what we might expect to see is an undefined value for the slope. So let's confirm that that's what this derivative provides us. So we'll consider 1, 1. So we want to evaluate. We'll want to evaluate dy dx at 1, 1. And so that would be dy dx at 1, 1. And so just basically plugging in 1 for x, 1 for y, you'd get 2 times 1 up top. And then below, if you recall, the function is 3 times 1 squared plus 2 times 1 minus 5. What happens here? Up top, I get a 2. What do I get down below? I get 3. So 3 plus 2 minus 5. Oops. Uh-oh. Right? So I get an undefined. I get an undefined slope at the point 1, 1. Now that's what we expected, right? We expected that would happen, and we just showed that it happened. Right here, the slope of the tangent line of this graph would be vertical. All right. And so on, right? And so you could go around kind of testing various points and see what happens. And in fact, the equation the value that we found for dy dx does tell you the slope of the tangent line at any point for the equation. Okay, let's try another example. Here, let's just be real explicit in what we want to say here. Let's determine the slope. We want to determine the slope of the tangent line to the graph of, and let's say x squared plus 4y squared equals 4, right? So determine the slope of the tangent line to the graph of x squared plus 4y squared equals 4 at, and here's the point, let's say square root of 2, comma, negative 1 over square root of 2. All right. So if we graph this equation, it's not a function again, but if we graph this, what do we get? Well, it's kind of like an oval sort of shape, right? So it cuts through, looks a bit like this. This isn't a great drawing, but it's right. So you could probably tell by the form that it's going to be something like a circle, right? And it looks a bit like this, right? So it's kind of an oval shape. Right, and then the point we're interested in is the square root of 2, so that's like a little bit positive. That's a little bit past 1 on the x-axis, and then it's negative 1 over square root of 2 over 2. So it's going to be like roughly this point here that we're interested in. We want to know the slope of the line that cuts through that point, the tangent line that cuts through that point. All right. Well, so we can do this, right? So we've got the equation. Let's just go ahead and implicitly differentiate this to start with. So it'd be d dx of x squared plus 4y squared, and that's going to equal d dx. That's terrible handwriting, of 4. Okay, differentiate both sides with respect to x. And so that's going to be d dx of x squared plus 4 d dx of y squared, and then we'll just differentiate this quick. That's a 0 over there. And so then you get, what, 2x here plus 4 times 2y times dy dx, right? Right, so here again, just because this is kind of the new thing, right? So we're differentiating y squared with respect to x, so you get the 2y on the outside, and then you've got to use the chain rule, so you would differentiate the y variable itself, and that's dy dx. Okay, and so then what we can do is we can kind of, let's clean this up just a tish. So you'd be 2x plus 8y dy dx equals 0. And we want to solve for dy dx, right? And so that means you've got 8y dy dx equals negative 2x. Right, kind of bringing that over the other side. And then you've got dy dx equals, now what is it? Negative 2x over 8y, right? So negative 2x over 8y. And of course we can simplify that, and we should. Dy dx equals negative x over 4y. All right. So this is our derivative, right? So we started with this equation here, which is obviously it's not explicitly written, y is not explicitly written as a function of x, and indeed we can plot this thing and we can see this is clearly not a function. And so we start with that, but we want to know dy dx, and so we can calculate dy dx using our implicit techniques, and here's the derivative that we get. Now what we're interested in is we want to know the slope of the tangent line at this point, square root of 2 comma negative 1 over square root of 2. So let's plug that in. So how do we do it? Well, we evaluate dy dx at, and I'll just write this in here, square root of 2 comma negative 1 over square root of 2, like that. And so then it's going to be negative square root of 2 on the top, and then it's 4 times negative 1 over the square root of 2 in the denominator. Okay, and so we can do some simplification here. Let's see here. So how much time we want to spend on this? We can do negative 4 divided by the square root of 2, and then you kind of unwind this fraction of fractions. You would say negative square root of 2 over 1 times square root of 2 over negative 4, like so. And the top, you actually end up with a negative 2 there, divided by negative 4. And so what do you get altogether? You get a half. You get 1/2, right? So when you ultimately, the value of the slope must be 1/2. And so when we look at this expression, well, that's certainly, I can buy that. This is a bad picture, but that squares with intuition, right? We would expect to get something like this. Now what happens here, right? We're going to get an undefined slope there. So if you plugged in the value of 2, 0 into this, right, you don't even have to do much to see that you would definitely get, an undefined slope here. So it'd be 2 divided by 0, so undefined, right? So you're going to get an undefined slope at 2, 0. Here I would expect that the value would be 0, and of course it is, right? Because this would be like the point 0, 1. If I plug in a 0, 1 here, I get negative 0 divided by 4, so 0. And so the slope is 0 there, right? And so everywhere in between, this works. All right, very good, very good. Let's do some more examples of, kind of some trickier implicit equations and trying to find the derivative. So we'll start with just some simpler examples. So here's one. What about sine of y equals x? Can we differentiate this? Yeah, this one's pretty straightforward, isn't it? So d dx of sine of y equals d dx of x. And so how do we do this? Well, the derivative of sine we know is cosine. And so this would be like cosine of y, and then we got to differentiate the y, and it'd be dy dx. All right, so let's put that in parentheses. And then, of course, this side is just 1. Okay, so then that would mean that dy dx, in the case of sine of y equals x, is equal to 1 over cosine of y. Okay. Very good. So that one's pretty straightforward. What about something more complicated? How about this? So 3, and then it's x squared plus y squared squared, okay, equals 100 x times y. All right, so this one is going to be a lot more involved, right? You can kind of see that. So you've got chain rule, plus you've got implicit differentiation inside of a chain rule. Not a problem though, we can do this. So again, we'd start by just differentiating both sides with respect to x. And I really recommend people actually write this out. It is the case when you're doing complicated derivatives that just writing the function out, actually the act of actually writing it, familiarizes you with it more than just looking at it. It's sort of a weird thing, but it's true. Okay, so then let's think about this side first. So we've got the 3, that's a constant, that'll just be out front no matter what, we don't have to worry about that. And then this piece here, you've got the chain rule, right? You've got basically the power rule, and then you've got an inside function, x squared plus y squared. Okay, so let's start with that. So just putting the 3 out front here. Then I'm going to bring the 2 down, and this is going to be x squared plus y squared, and then I'm going to write it to the first power just to make it clear what we're doing here, right? And then I have to differentiate the inside piece, right? This part. So I'll just do this in the next step, and I'll just write it out. X squared plus y squared. Okay, so that's this side. Okay. Now the other side, you've got this constant 100, so I'm going to bring that out. And then you've got basically the product rule, which we've seen the product rule already. So it'll be x times ddx of y plus y times ddx of x. And I'm just going to write everything out. All right, so there's no harm in taking a couple steps to do a problem, especially if it's a complicated problem with a lot of moves like this. So, okay, now coming back through and cleaning up what we haven't done. All right, so this part out here is all good. Now, how do I differentiate this? Well, this is just 2 terms that I have to differentiate separately, right? So the first term is really simple. It's just 2x. Second term, it would be simple as well, except the only complication here is that this is a y, and we're differentiating with respect to x. So it would still be 2y, but then because it's y with respect to x, we'd have to use the chain rule on it, and which basically amounts to putting a dy dx factor in there. So there we go. That's that side. And then over here, this is going to be x. And then the derivative of y with respect to x, well, that's just dy dx, nicely. And then plus y, and then that's just a 1, so we'll just leave it off. Perfect. Okay, now everything is differentiated. There's nothing left to differentiate. And what we need to do next is just sort of simplify everything. Okay, which might be a task here. Let's just see. Let's take a look. So let's multiply the 3 and 2 together here. So let's see, we've got a 6 out front. And then what do we got? Well, let's just rewrite this and get these constants sorted out. So y squared, and then this is 2x plus 2y dy dx. So we didn't make a lot of headway this pass, and then this is the same thing. So this is just 100, and then it's x dy dx plus y. So we really basically only cleaned up the constant that time. Let's do a little more of this with this pass. So I just basically got to FOIL all this out, don't I? So it'll be 6 times this times that. So actually, I'm going to do it in 2 steps again, just for the sake of the audience. So we'll put the 6 in there, just it'll be easier to keep track of it. And there we go. And now we can just FOIL this out. So it'll be 12x cubed. Okay, so that's the outsides, plus 12x squared. Hold on. Yeah, so plus 12x squared times y times dy dx. So we did the first, and then we did the outside, and now we've got to do, let's say, the inside. So that'd be plus 12xy squared, and then the last terms, which would be plus 12y cubed dy dx. Perfect. And then on the other side, what do we have? We've got basically 100x dy dx plus 100y. All right, so it's a little bit of a, it's definitely going to fill the page here. And so then the key thing here, what we're really trying to do is get all the dy dx's together. And so let's do that. So you basically got this term here, and that term there. Let's get those all on one side. So what do we have? We've got 12x squared y dy dx, so that's that one, plus 12y cubed dy dx, that's that one. And then this guy we're going to bring over, so it'll be minus 100 dy dx. Right, so we've got, that takes care of that, and that. And now we're going to move everything else onto the other side. Right, so we've got the 100y over there. And then I need to subtract 12x cubed. And I need to subtract 12xy squared. All right, so now everything is sorted out. We've got everything kind of on the correct side here. And so then it's a simple matter of just factoring all these pieces out, right? And then you have dy dx times those three terms, right? And then you would divide it all down. So in the end, what you get is 100y minus 12x cubed minus 12xy squared. And then you're going to divide by these three. 12x squared y plus 12y squared minus 100, right? And so this is what the derivative looks like for this more complicated expression. So we started with this, and here's the derivative. Okay, very good. All right, so that's a nice tricky example. Let's do one more tricky example. And this time, let's actually find a slope too. So let's. Here's the expression or the equation: x squared times x squared plus y squared equals y squared. Okay, so that's the. We'll say that's the equation. We want to find dy dx. And then find the slope of the tangent line at, and then let's use square root of 2 over 2, comma, square root of 2 over 2. Okay, so this nice point here. All right, so we need to find the derivative first. So we're going to differentiate both sides with respect to x. So it'll be x squared and then x squared plus y squared. Find that derivative, and that's going to equal d dx of y squared. All right. So, there's a couple ways you could do this, right? I think probably the most straightforward way is to rewrite this without, by basically distribute the x squared through here. Because then it's a straightforward matter, a relatively straightforward matter. You could also keep it like this and note and recognize that you've got a product here, and then you could use the product rule. We're going to end up using the product rule anyways, but I think just for the sake of making it structurally a little easier to look at right now, it might make sense to just multiply this through. So you get x to the fourth plus x squared y squared, and that's going to equal d dx of y squared, right? Now here you can see the product rule is going to be inevitable here. We have to use it. We also had to use it here. So either way, you're going to have to use it, so let's just do it this way. All right, so then we just differentiate each of these terms. So it'd be d dx of x to the fourth plus d dx of x squared y squared equals d dx of y squared. Right. Now again, I'm kind of being very intentional with the way I'm writing this, taking putting all of the steps in. I certainly think you could have jumped from here directly into this derivative, and this derivative could have been dealt with a while back, but just kind of keeping everything like really concise isn't the name of the game here, right? The name of the game is to show every single step and to make it clear what every little step is about. Okay, so at this point, everything's kind of in, let's differentiate these two outside pieces anyway. So 4x cubed, right? And then over here, we'll differentiate that when we get to it. But this is the product rule, so let's write that out. So it'd be x squared times d dx of y squared plus y squared times d dx of x squared. Okay, so that's this guy. Okay, and then that equals, and let's just do this one, it'll be 2y dy dx there. And I think we can get this all in one more pass, so it'll be 4x cubed plus x squared times 2y dy dx plus y squared times 2x equals, and then over here, 2y dy dx. All right. Okay, so all the derivatives are done, right? The differentiation part of it is done. Now it's all just a matter of, can we explicitly write dy dx? And yes, we can, right? It's just a bunch of terms. We can divide it out. So let's we got to get this guy and this guy on one side, and then this guy and that guy on the other side. Okay, so let's do that. X squared. So I'm going to write this as 2x squared y dy dx. That's this one. And then minus 2y dy dx. Okay. And that's that one. And that's going to equal these other two, but on the other side of the equation, so everything becomes negative. So it'll be negative 2xy squared. That's that one. Minus 4x cubed. That's that guy. And so then we can factor dy dx here out. And let me just make sure that that's coming across. So I'll just do it so people can see. I kind of skipped that step on the last example. I want to make sure people aren't missing that. So minus 2xy minus 4x cubed, right? So here I just factored this and this out of these two terms, and that's kind of the way it works in the end here. So then it's dy dx equals, and you can divide everything down, right, by this. So negative 2xy squared minus 4x cubed divided by 2x squared y minus 2y. Okay, looks good. Okay, so that's the derivative of y with respect to x of this guy here. Okay, so we found, so step one done. Now what we want to do is we want to identify the slope at this point, right? So this point is apparently a point on the slope of the graph of this equation, and we want to know what the slope is at this particular point. And so how do we do that? Well, we just plug it in, right? We just evaluate the derivative at that point. So it's dy dx evaluated at square root of 2 over 2, square root of 2 over 2, just like that. And it's not going to be pretty, but let's see if it cleans up. So it'll be negative 2 and then square root of 2 over 2, square root of 2 over 2 squared, minus 4, and then it's square root of 2 over 2 cubed. Okay. And then it's 2 square root of 2 over 2 squared times the square root of 2 over 2 minus 2 times the square root of 2 over 2. So it's a lot of square root of 2's over 2's there. And I'm not going to do it, but here's what I'll say, and I encourage you guys to do it. Just spend a second when you crank all this out, like you can see here that the square root of 2, anytime you square that, it's going to just be 2, right? So this is 1, for example, as is that, that's 1, right? And then when you cube it, you get 2 square root of 2, so this would just be square root of 2. So all together at the very end, the answer is 3. And I did the work, but I think I'll leave it to you to confirm that that's the case. All right, very good. So that's it for this section. Again, the main story here is that given an equation that's not, in explicit form where you have y written explicitly as a function of x, we can still find derivatives, right? So given something really messy like this that can't be converted easily to an explicit form, we're not totally stuck. We can still calculate derivatives. We can still use the features of the derivative, i.e. that it tells you the slope of the tangent line at the points on the curve. We can still do all of that stuff even in the cases where we don't have actual functions. So it's just a powerful add-on to calculus. So, all right. So next time we'll get into inverse functions and start talking about derivatives of inverse functions.